Okay, so obviously this will be in your notes package, okay, and just so you get some idea of what that notes package will look like for you guys. So you may just want to make some jot notes today as we go through, but okay, the notes package, you won't necessarily get all the diagrams and stuff like that. You'll get any diagrams that are super important, okay, but you won't necessarily get all the little pictures that I put in, okay, but you do get all the same text. So within your notes package, okay, it's broken up into the lessons that I will teach, and each lesson starts with key points, okay? Those are important because they can help you to focus your studying and review later. Okay, they basically tell you here's the 2 big things or 4 big things from this unit or from this lesson, sorry, that'll be on the exam, okay, or that have the most impact on this unit. So those are the things you want to make sure you cover, highlight if you're a highlighter. I used to be a highlighter, not like the actual marker, but a person who did that. Okay, yeah. So those are kind of things that you might want to focus on. Okay, so for this first lesson, okay, the key points are that we have to understand how the theories of the structure of the atom were developed. Okay, and learn the parts of the atom and their characteristics. Hopefully, that's going to be a review for you. All right. So your notes package will look like that. Come on. I don't know why none of the Google stuff is working on my here today, but okay, so like I say, if there's an important diagram, important diagrams will show up in the notes package, okay? So there are some pictures in there, right? But that's what your chemistry notes package essentially looks like. Okay, so like I said, you don't need to print it in color. You got the color versions here. You can always look up the color versions online because I'm going to post them, okay, in Google Classroom. All right. Okay. So back to this. Okay, so like I said, key points for today, understand how the theories of the structure of the atom were developed and learn the parts of the atom and their characteristics. Okay, so chemistry wasn't always like a true science. Okay, it started out with a group of people who basically were experimenting with things, but it was all trial and error. There was no scientific method or anything like that. Okay, but people realized that things in nature could do certain jobs or had certain properties, okay? And so we would call those either physical or chemical properties, and they learned what these were and how to use them for their benefit, okay? And that was kind of the start of the knowledge that built and became chemistry. Okay, so long before the science of chemistry existed, people made use of these things. Chemical reactions dyed cloth, or cooked food, or prepared or cured or preserved food, things like that. Okay, eventually people began to search for explanations for the structure and behavior of matter that they were using. Okay, now the idea of the atom has actually been around for a very, very long time, but it was not accepted until far more recently. Well, recently in terms of history, so a couple of hundred years. But okay, originally, especially the Greeks believed that all matter was made up of 4 elements. Okay, what were the 4 elements? And water. Okay, earth, wind, fire, and water. Or earth, air, fire, and water. Okay, those were the 4 elements. Okay, and it was a very logical conclusion for them to have. Okay, because they could see those 4 things in most of the matter they encountered. Right. As an example, steam would be some parts fire, some parts water, and some parts air, because those are the 3 things that go together to make it. Right? You take water, you put fire underneath it, and it evaporates, it becomes steam. Okay? It made sense to them. Okay? If a volcano erupted and lava was flowing down the mountainside, they would run away and then from a distance look at it and go, well, lava must be some parts fire and some parts earth and some parts water because it's a liquid, but it comes out of the earth and it's hot. Okay, so these were things that they could explain and make sense of. Okay, it didn't matter that what it was made out of, like in terms of whether it was made of small, tiny particles. Okay, these were things that they could explain and made sense. Right, which was why this poor guy named Democritus, his idea was rejected. He was the first atomist. Okay, he was a thinker, which was like the best job you could have in ancient Greece. Okay, being a thinker meant that you got to sit in a Parthenon and people would like fan you with the big palm leaves and feed you grapes, and all you had to do was like come up with cool ideas. Okay, like Plato was a thinker. Okay, those kind of guys. So it was a good job to have. Like, it was the best one. Yeah.
Plato was an actual guy.
Yeah, Plato was an actual guy. Yeah. Okay, so Plato, Aristotle, those guys, they were all thinkers, right? And their idea was that it was the earth, air, fire, and water, especially Aristotle, right? And so they were a little more, widely thought of than Democritus. So his idea that matter would be made of these tiny, invisible particles was kind of, they're like, did you eat a bad grape? Because that idea doesn't make a lot of sense. Maybe you should come up with something else. Okay. Ironically, though, he was correct. Okay, in that matter is made of tiny particles. They're not invisible, but they're indivisible. That means they don't break apart necessarily on their own, right? So his idea wasn't really discussed for about another 2,000 years when people started realizing that matter does behave like it's made up of these tiny little particles. Okay, so his ideas were overshadowed by more famous philosophers and thinkers, so it kind of just was forgotten. Okay, but it wasn't all bad for Democritus because he did come up with some pretty good ideas. What does his name sound like? Democracy. That's him. That's the guy. Okay, so it wasn't all bad for him. Okay, he did come up with some good things. Okay, now skip ahead 1,000, 1,500 years or so. Okay, to the kind of the Middle Ages. Okay, we say chemistry reappeared. It's not true chemistry yet because again, it's trial and error. And the most important part of any true science is communication. Okay, you start testing something, you come up and you run the scientific method, you have a problem, you have a hypothesis, you have materials and a procedure, and then you communicate your results with your peers, and your peers try to replicate your research. And if your peers can all replicate it, then then your idea or your hypothesis is acceptable. Okay. Early chemistry was known as alchemy, and that communication was not present because alchemists were trying to do things that are impossible. And they were very secretive about what they were doing because they didn't want anyone to find out, okay? Or if they figured out how to do something, they didn't want anyone else to learn how to do it because then they wouldn't get rich, right? So they were trying to do things like change lead into gold, okay? Transmute lead into gold, which is impossible, okay? You can't turn one element into another element. It just doesn't work, okay? They were trying to come up with the elixir of life, okay? Something that you could drink that you'd live forever. Okay, things like that. They thought things like mercury and stuff would be good for that. So like lots of people were poisoned in the process of this whole thing. Okay, I'm sure like they probably discovered gunpowder about 10 or 11 times, but never lived long enough to tell anyone because they blew themselves up. Okay, they were very secretive, okay, about all of their stuff. So they would have a lab, kind of like Da Vinci's lab here, right? They'd be filled with all kinds of strange shaped glass containers and mortars and pestles and all kinds of stuff like that. And they'd be hunched over their thing with a candle and mixing stuff together to see what would happen, right? Now, not to say that it wasn't useful. A lot of stuff was learned. The problem was it didn't get put out there into general knowledge, okay, and for people to gain something from it. So it took these two guys to kind of make alchemy into a true science, okay? So this is Antoine Lavoisier and Roger Bacon. They are the two scientists credited with coming up with the scientific method. All right, so that's what we talked about before. You have a problem, you come up with a hypothesis for why that problem is happening, okay, and then you develop a procedure to test it, you analyze your results, and then you make a conclusion that says your hypothesis was acceptable or rejected, and then tell people why, okay? That was kind of their contribution, and that's what turned alchemy into a legitimate science, okay? It took it from trial and error to something more practical, okay? Okay, so if we take a pure substance, like let's say a chunk of lead, all right? If you take that and you start cutting it into smaller and smaller pieces, do all the pieces still have the same properties, other than size, obviously? Yeah, they do, right? Every piece I cut is still lead, right? I'm not changing the chemical nature of the substance by making it smaller and smaller and smaller. Right? And that's kind of the idea behind the idea of the atom, is that a substance is made of these tiny particles, and each particle has the same properties as every other particle of that material. Okay, now if I had a particle of lead and a particle of oxygen, they would be different, and that's why oxygen's a gas and lead's a solid, and they have a lot of things that are different. Okay, so If we start cutting it down, we get smaller and smaller gray metallic pieces, okay, but they still retain the properties of lead, and eventually you'd reach a point where you couldn't cut that piece any smaller without actually changing what it was. Okay, that would be you're now down at a single atom. Okay, if I was to actually be able to split that atom, would it be lead anymore? No, because now I would have two smaller atoms. Okay, would have a different number of protons and a different number of electrons and neutrons and all that. It would be actually something different. Okay, and in a nuclear reaction, that happens. Okay, when you actually split an atom in nuclear fission, your end result is different atoms. All right, not a lot different, but different atoms because you've broken pieces off. Okay, and now they are actually physically different. All right, can we do that with a knife? Yeah, it's a good thing too. Imagine if you're, at home and you're, chopping up a carrot. You don't necessarily want to split the atom while you're doing that. Okay, be bad. Okay, so you can't do that. Mainly because, well, a knife is like hundreds of thousands of atoms wide, even on the sharp side. All right, it's atoms are incredibly small. You're not going to split one with something that's 100,000 times bigger than a single atom. Okay. All right, so the smallest particle is an atom, okay, and it's the smallest particle that retains the properties of that particular element. So that part there, okay, I would say that might be something you want to jot down. All right, so when you get your notes package printed, that's something you'll want to highlight, okay, and have for yourself. Okay, quick review, structure of the atom. What's this big thing in the middle called? Okay, so that's the nucleus, because we use the nuclear model, okay, of the atom, one that has a nucleus. All right, and within the nucleus, we see these yellow particles with the plus sign. They would be, okay, what are the orange ones? Neutrons, and the ones that go around the outside? Electrons. Now, do they go in a circle like this? No. Okay, the modern model of the atom, the electron cloud model, okay, that we use, or the quantum mechanical model, okay, says that electrons actually move all over the place. They may have some type of orbit, but that's based on their energy level, okay, and they can actually jump and fall from one energy level to another based on the level of energy of the atom, okay, so yeah, they don't orbit like planets around the sun. Okay, that planetary model was accepted for a while, but we learned that that's not actually how they function. So we accept a slightly different model. But still, the nuclear model is still part of that. There's a nucleus, and electrons surround the nucleus. Okay, all right. So the first person to kind of resurrect Democritus's idea of the atom was Dalton. Okay, John Dalton, and he is credited with developing and proposing the atomic theory. Okay, so Dalton's atomic theory consists of 4 points. Now, Dalton came up with these points as a result of basically a lifetime's worth of work in chemistry, okay, in looking at reactions and what the products, what the reactants, the starting materials and products of those reactions were, okay, the behaviors of the materials during a reaction, what's going on, what do I produce when I start with this, what do I produce when I start with something different, okay, it was a lifetime's worth of work, and what he discovered was what he put into this theory, okay. First point is Democritus's point, okay, all elements are composed of tiny, indivisible particles known as atoms, okay? Now, this is not, we need to make sure we use the right word here. This is indivisible, not invisible, okay? Invisible means people can't see you, okay? And while, yeah, we can't see atoms, it's not because they're invisible, it's just because they're really, really small, okay? Indivisible means I can't physically divide them, okay? If I have a single element, I can't physically divide it, okay? It's not gonna just come apart. Okay. If I have certain types of atoms, I can split them through a nuclear means. All right, but that's pretty artificial. Okay. All right. So are they divisible? Yeah, if you have the right equipment. Okay. For most of us, no, they're not. Okay. His second point. Okay. Atoms of the same element are identical. All right. That's crucial. It's And for the most part, it still holds true. Okay, when we learn about isotopes and things like that, we will find that two elements of oxygen could have slight differences in the number of neutrons. Okay, but okay, they do always have the same number of protons, okay, in the nucleus. So atoms, all oxygen atoms are effectively identical. All atoms of lead are identical. Okay, but atoms of lead and oxygen would look different. Okay, so atoms of the same element are identical. Atoms of one element are different from those of other elements. Okay, that's what makes them different, is that their atoms look different. All right, and actually on that note, I'm going to give you a periodic table. All right, so now that you got a periodic table, you can see on there, okay, that every element has a different number in the top left corner. Okay, that number in the top left corner is the atomic number. It is the number of protons in the nucleus of that atom. Okay, so basically it's the number of protons in the nucleus that determines the physical and chemical properties that that element will have. All right, third point. Okay, the third point talked about kind of what happens in a chemical reaction. All right, Dalton had run lots of chemical reactions and had realized that when you put two things together, you do end up with something new, but it's still made up of the things you started with. Okay, you're not turning one thing into another. That was where the alchemists had it wrong. Okay, because they were always, like we say, trying to turn like lead into gold or cheap materials into more expensive materials, because when they mixed things together, they realized that when there was a reaction, what they had at the end was different. What they didn't realize was it looked different, but it's still made up of the same things they started with. They didn't actually create anything new. It was the same elements, just rearranged. Okay, and kind of follow me on that? Like when you're in like grade 5 and you mix like vinegar and baking soda together, all right? When you finish, you have like carbon dioxide and sodium acetate and some water. Okay, well that's not what you started with. You started with acetic acid and sodium hydrogen carbonate. Okay, but when you look at all the atoms, all the elements that are on both sides of that reaction, it's exactly the same elements. Okay, we created different materials, but we still have the same elements that we started with. Okay, so it's actually Dalton's third point here that kind of put the death blow to alchemy. Okay, that you can't transmute something into something else. Okay. All right, so elements can combine with one another in simple whole number ratios. That's also important. Okay, simple whole number ratios, not half an atom or a quarter of an atom. It's always full atoms. Okay, so if you're looking at something simple like water, right? It's 2 hydrogen atoms and 1 oxygen atom, right? I wouldn't write it like this. Right? It's the same ratio, right? It's still 2 to 1, but I can't have half an oxygen atom. Half an oxygen atom is something else because it wouldn't have the same number of protons. Everybody kind of follow me there? Okay, so always in simple whole number ratios, 2 to 1. Okay, you never have a piece of an atom. Okay, you always have whole atoms. And then the fourth one, okay, talked about again what happened in a chemical reaction. So this is supporting point number 3. Okay, chemical reactions occur when atoms are separated. Okay, so if I was to pull the hydrogen and the oxygen in water apart, okay, that would be a decomposition reaction because I'd be breaking down a compound. Okay, or they're joined. Okay, so if I was to put two things together, they reacted with each other and formed a single compound. Okay, in a synthesis reaction, that would be, okay, again, joining two atoms. Okay, or they're just rearranged. Okay, however, atoms of one element are not changed into atoms of another element. So you can't change lead into gold. Okay, so if we had like a kind of a more complex reaction, like let's say we had this one. So we have. Okay, so I'm going to mix copper with silver nitrate. This is something we'll do later, but just to kind of illustrate what Dalton was saying here. Okay, here's an element, and it's reacting with a compound. All right, when this is all done, okay, you end up with silver and copper to nitrate. Okay? This is the kind of reaction that could have been run by an alchemist and would give them the idea that they could turn one thing into something else. Okay? If they took a bunch of copper, which would have been cheap and readily available, okay, and mixed it with silver nitrate, they would get silver out of that. And it would look like the copper had turned into silver. Okay? If you take a piece of copper wire and you immerse it in silver nitrate, okay, you come back the next day, that copper wire will be plated with silver. So it'll look like you turned the copper into silver. Okay? This is where they got kind of their misleading ideas about what they could do with chemistry. Okay? They didn't realize that they had silver all along. They just didn't know it. Okay? It was there all along. Everyone kind of follow me on that? Okay, so yeah, this is going to look a lot different than what they started with, but it still contains all the same materials that they started with. Okay? All that's happened in that reaction is atoms have been rearranged. Okay? They have new partners. All right. So, are the 4 points of Dalton's atomic theory something that probably would come up again later, like on a quiz or a test? Definitely. Okay, so you definitely need to know those. Okay, the 4 points of the atomic theory, okay, are crucially important for you. All right, be really easy to make like a multiple choice question and say which of the following is not part of Dalton's atomic theory, and have 3 out of the 4 of these. Okay. Okay. Anybody still need that? All right. So Dalton comes up with this theory, and then the next natural question for him is, okay, that sounds good. What do your atoms look like? And the natural response to that is, well, they're so small you can't see them, so I don't know. And everyone's like, well, that's kind of a cop-out. Okay? Can't you give us some idea? You got some idea what they look like? And in all honesty, Dalton didn't know. They were too small. So he said, they're probably a sphere. It made sense. Lots of things in nature were spheres. The sun, the moon, the earth, okay, all of them are spheres. By the way, the earth is round. Okay? If there's any of you flat earth people out there. Okay? Yeah, the earth's not flat. Okay? You see that guy who launched a rocket the other day? He was trying to prove the earth was flat and the rocket blew up. Okay? Earth's round. Okay, so he said atoms are probably a sphere, which for the time was a pretty logical conclusion. We didn't know about protons yet, didn't know about electrons yet, okay, didn't know about neutrons, none of those, right? It just made sense that they're really, really small and they're probably shaped like a sphere, okay? It's a natural reaction, and people accepted it because there was nothing to say he was wrong. We know now he was, but okay, at the time, it was a reasonable assumption, okay? So the first atomic model is what we call the solid sphere. And it lasted for a while until people started discovering new things. All right, so a guy named J.J. Thompson in 1897, okay, so a little over 100 years ago, okay, was doing experiments with what we call now electrochemistry, essentially trying to improve and make a good battery. Okay? And what he noticed was when he was performing these reactions, that charged particles would move through a wire. I mean, that's what we want batteries to cause, right? Is for electrons to move through a wire so they can power our devices. Okay, but what he was trying to explain was, where are these charged particles coming from? I mean, it's all well and good that I can make this happen. I'm going to get rich on the fact I can make this happen. But why is it happening? Okay, that was the question. If atoms are solid spheres, what part of the atom is traveling through the wire? It can't be the whole atom, because if it was, what would happen to the wire? Do atoms have mass? Yeah, so if atoms are moving through the wire while electricity is being conducted, then whatever you start with should get lighter and smaller, your wire should get bigger, and wherever it's going to should also get bigger and heavier. Okay, well, that's not the case necessarily. I mean, to an extent, right? How many people know how you test whether a small battery is dead or alive? Bounce it. Yeah, okay, because electrons move from one part to the other. Now, electrons aren't very massive, but okay, it causes changes in the nature of the distribution of mass within the battery. Okay, a live battery, if you drop it, not very much, like drop it from here. Okay, like drop it maybe an inch or two. You drop it, it'll stand up. A dead battery will fall over. Okay, because things have moved around within the battery and change the distribution of mass within the battery, so it'll fall over.
Will that work with the car battery?
No, because the car battery is a wet cell. It only works with a dry cell. Well, you shouldn't drop a car battery. It's full of acid. Yeah, you could splash or break or bad things. They're very heavy too. You drop it on your foot. Yeah. Okay. So yeah, it works with the little dry cells. But okay, he was trying to explain how that fit with Dalton's solid sphere model, and it just didn't. Okay, there was no way that Dalton's model of the atom being a solid sphere could explain where these charged particles were coming from. So he modified Dalton's model. Okay, and he came up with atoms are like plum pudding, whatever that is. Apparently, it's like a solid mass with plums embedded in it. Okay, it doesn't sound very appetizing, but okay. Anyway, he said that's what an atom looks like. And the plums are these little particles that I'm going to call electrons because they're the source of electricity. Okay, didn't really know much else about them. Okay, but they were the source of electricity, so they're called an electron. That's why they're not called a negatron. Okay, now we know they're negatively charged, but they got their name before we knew that. Okay, so they're called electrons. Okay. And so what he said happens is in a reaction, the atoms hit each other and the electrons can fall off. And when they fall off, they can go through a wire to a lower energy state on other atoms. Okay, and that was a reasonable conclusion. Okay, it explained where the electrons were coming from and where the electric current was coming from without really tearing apart Dalton's model too much. Okay, everybody kind of with me there? So we come up with these models because the previous model is no longer explaining things we've discovered. Okay, and when that happens, we have to change our model. We have to change our way of thinking. That's how science works. Okay, it's why very few things are like irrefutable laws. Okay, there are very few irrefutable laws in science. There are lots of what we call theories. Okay, and a theory is something that's been supported by evidence for a very long time. Okay, so like we still say this is Dalton's atomic theory. We don't say it's Dalton's atomic law, right? We know that parts of it could change. Okay? There are things in there that we're learning all the time, right? So we call it, it's a theory because it's holding up, it's held up under scrutiny for 100 years or more, okay? But it's not an irrefutable law, okay? So that was J.J. Thompson's plum pudding model. So I would say probably a good idea to know his name, okay? He discovered the electron, okay? And came up with the plum pudding model. All right, we'll pick up right there tomorrow. Okay, have a good rest of your first day of high school.